Till now, we have studied linear elastic fracture mechanics, LEFM. LEFM is applicable to high strength materials and the materials that have low ductility. Because of low ductility of the material, there is a minimal size plastic zone at the crack tip. And because of this reason, there are very high stresses that are generated near the crack tip. And because of the very high stress level at the crack tip, crack once formed, it propagate rapidly and result in catastrophic failure of the brittle material. Now if we see the stress profile of the material as we move away from the crack tip, there is a reduction in the stress, and far away from the crack tip the stress is same as that of the applied stress. This is the stress profile. Now why we call it linear elastic? That is because the curve between the load and the displacement, it is linear. However, for elastic plastic materials, the curve between the load and displacement, it's non-linear, and upon unloading it do not trace the same path, it rather follow a different path. And for these elastic plastic materials, basically they have high ductility and generally low strength. So these kind of materials that have high ductility or elastic plastic materials, they have plastic zone at the crack tip, and because of the plastic zone, the stresses at this plastic zone that are near yield strength, and far away from the crack tip the stresses are same as that of the stresses applied on the material. So just after the plastic zone there is a reduction in the stress level. So in order to determine the fracture toughness of elastic plastic materials, there are different models. First of all, Irwin suggested that K-modification can be done, stress intensity factor. He suggested that we can write K equal to sigma root pi A effective. So A effective is A plus RP. We can see this is the crack length A, and here there is a plastic zone that is RP sized. And the second model was given by Dugdale. He proposed that if there is a crack of length 2A, then there are plastic zone near the crack tip in the form of narrow strips, and that are of length R. So the whole crack length will be 2A plus R, and these plastic zone will close the crack tip when compressive stresses are applied normal to the surface. Based on this assumption, he proposed an equation to determine the plastic zone length, that is pi square sigma square A divided by 8 sigma y square. Here sigma is the applied stress, A is the crack length, sigma y is the yield strength. And we can write pi k square because we know k is equal to sigma root pi A. And this will be 8 yield strength square. Now here we can see it's K, and here also Irwin has also used K term. K modifications can be done when RP is less than A. RP is very small compared to crack length. In that case we have small scale yielding, and in that case K modification can be done. However, when RP plastic zone size is greater than crack length, in that case it's a large scale yielding. And for that case we have two models. One is crack opening displacement and the other is J integral.